Thank you for the introduction. I'm Yixin from Princeton University, and today I'm presenting our work on RAPTOR, safeguarding Tor against active routing attacks. And this work is done in collaboration with Annie Edmondson, Nick Finister, Meng Chang, and Pratik Mittal, all at Princeton University. Internet communications are not anonymous. So consider this simple case when a user visits a website. The ISPs learn the destination identity of the site that the user is visiting. And on the other hand, the destination also learns the source identity, which is the user. Furthermore, anyone that's able to eavesdrop on this internet communication can learn the same information by simply looking at the IP headers. And this problem remains even if the communication is encrypted. To counteract the problem, anonymity systems such as Tor have been designed. Tor provides anonymity by hiding IP headers and prevents attackers from associating the source with the destination. Tor does that by relaying traffic on top of an overlay network composed of 3 types of relays, as shown here. And the Tor client selects 3 relays, 1 of each type, to build a Tor circuit. Anonymous communication takes place by forwarding traffic across these consecutive tunnels, so that no single entity in the middle of the process can know both the source and the destination at the same time. However, Tor is known to be vulnerable to traffic correlation analysis. The traffic entering and leaving Tor is highly correlated, so an AS-level adversary who is on path at both ends of the communication, as shown in the graph here, between the client, the guard, and between the exit and the server, he can perform statistical correlation analysis on the packet traces at both ends and de-anonymize the users. But what if an AS-level adversary that's not currently on path and yet still wants to observe the Tor traffic? And that is our focus, active attacks on Tor. That an adversary can launch active BGP routing attacks to get himself on path and observe the Tor traffic. These kind of routing attacks enable on-demand and fine-grained attacks on the Tor network. And here's a really simple example. It's a partial internet topology, and the AS3 here, that's our malicious AS, and he wants to observe the Tor traffic that go into the guard relay, which is in AS1. So he's announcing the same /16 prefix that AS1 is announcing and trying to get the traffic routed to AS3, the attacker, instead of AS1, which has the guard relay. So this is a really simple example of what's a BGP hijack. And these types of BGP attacks are real, and they have already affected Tor network in the past. This is a news article in April 2014 that Indosat, which is one of Indonesia's largest telecommunication providers, leaked more than 320K BGP routes over 2 hours. Among the victims, there were also 44 Tor relays, and 38 of which are guard relays that actually had direct connections with the Tor clients. These kind of active attacks motivated our work on RAPTOR, safeguarding Tor against active routing attacks, and we made 3 contributions in our work. First, we performed a measurement study in order to understand the vulnerability of Tor to this kind of active routing attacks. We then designed a new Tor guard relay selection algorithm to proactively defend against these attacks. We also developed a live BGP monitoring system as a reactive defense. So first, I will go into the measurement study. Tor connections get routed according to BGP. This is a simple AS topology. We have 2 Tor clients here. The Tor client 1 is in AS2, and another Tor client 2 is in AS4. And they both use the same Tor guard relay that's in AS1. AS1 is announcing the /16 prefix, and the traffic get routed to the Tor guard relay in AS1 based on this routing announcement. Now, our bad guy, AS5 here, he wants to hijack the traffic to the Tor guard in AS1. So he's announcing the same /16 prefix to its neighbor, let's say AS3. AS3 then further propagates the announcement to more neighbors, including AS4. So at this point, as you can tell from the graph, the traffic diverges on the internet. For our Tor client 1 here, that is in AS2, he is actually resilient to this attack because AS2 still prefers the route announcement, the path to the true origin AS, that is AS1, and still sends the traffic to the real guard relay. Whereas AS4, where the Tor client 2 is, AS4, on the other hand, prefers the route to AS5, the attacker AS, instead of AS1, which is the true origin AS that has the Tor guard. And as a consequence, the Tor client 2 is not resilient to this attack. And this example illustrates the key insight in our measurement study, that we want to measure the probability that the Tor client AS is resilient to hijack attacks on its guard relay. Or in other words, we want to measure the probability that the Tor client would actually believe the announcement from the true origin AS, where the guard relay is, instead of the false origin or the attacker AS. We showed our evaluation for the hijack attack resilience, considering more than 52,000 ASs in total on the internet topology. We also identify more than 1,100 ASs that contain Tor relays as our potential victims of the attack. This graph shows the hijack resilience of each of these Tor-related ASs and their corresponding Tor bandwidth. We can see there are two clear outliers on this graph, OVH and online SAS. So they both have very high Tor bandwidth, meaning that they're handling and observing a huge amount of Tor traffic. Well, on the other hand, they both have relatively low resiliences to attacks compared to other Tor-related ASs. The next question we want to ask here is, okay, so can OVH and online SAS still be good choices for some clients despite their overall low resilience? And the answer is yes. This graph shows the hijack resilience of still OVH and online SAS, but across different clients. We can see that there's high heterogeneity in the hijack resiliences here. There are some clients for some clients, the hijack resiliences are really low with OVH and online SAS. That's in the lower left part of the CDF. But on the other hand, we have more than 20% of the clients that actually have very high hijack resiliences with OVH and online SAS. That's the upper right of the graph. So what this can tell us is that, and this also provides the key insight to our next part of the work, which is guard relay selection, that we should really consider this new notion of resilience when picking a Tor relay. Besides hijack resilience, we also presented the results for resilience to interception attacks in our paper, which is not presented here. So interception is actually a more sophisticated attack than hijacks. If you're interested, refer to our paper for it. I think that's also a very interesting measurement study. Next, I will talk about our new Tor guard relay selection algorithm. First question is, why do we focus on the guard? Because guard relay is at a very important position in the Tor network, that it has direct connections with the Tor client, so it knows where the client is. And also, the Tor client actually uses the same guard for an extended period of time, which is not the same as middle and exit, that are frequently changing and reselected for each new Tor connection. And again, the key insight we bring from the measurement study is that we want to choose a resilient guard based on the client location. This is how we incorporate resilience into the relay selection. For each guard relay, we're going to compute the new weight that combines the hijack resilience of the relay from the client AS, as well as the bandwidth of the relay. We also have this configurable parameter alpha that indicates how much weight we want to put on the resilience versus the bandwidth. And note that when alpha equals to 0, that's when we're not considering resilience at all. This algorithm becomes the same as the current vanilla Tor relay selection algorithm, that's bandwidth only. And as alpha goes higher, it means like higher weight on resilience opposed to bandwidth. This graph shows the probability of being resilient to attacks with different alpha values in the algorithm. And again, alpha equals to 0, that's the blue line on the left. It corresponds to the vanilla Tor bandwidth only selection, and you can see that the resilient probability is low in that case. But the interesting thing is that even with a very small increase in alpha value, like alpha equals to 0.25, there is already a clear increase in resilience to hijack attacks. And this increase can go up to 36% on average, that's when alpha equals to 1, and up to 166% maximum for certain clients. So it means that the algorithm benefits certain clients more than the others. For instance, if a client already has high probability of being resilient under the current vanilla Tor relay selection algorithm, then its space for improvement could be low. But on the other hand, for clients with low resilience, this algorithm could bring huge benefits. Next, we show the performance evaluation on our counter-RAPTOR algorithm. We use the shadow simulator, and we use the default configuration with 400 clients and 100 web servers. We evaluate the algorithm using alpha value equals to 0.5, so it means that we're giving equal weight to the resilience and bandwidth of the relay. This graph shows the download time for 320 kilobytes of data. We can see that there's not really a difference between vanilla Tor and our counter-RAPTOR in this case. This one shows a much bigger download size with 5 megabytes of data, and there is a small performance loss in the counter-RAPTOR compared to vanilla Tor. Finally, we present our live BGP monitoring system on Tor. The system does live monitoring on all routes to Tor relay prefixes. And the goal of the system is to increase routing transparency in Tor, so people can actually see how the routes are to all the Tor relays and notice if anything changes in real time. We also perform anomaly detection, again in real time, based on the routing data. We use 3 techniques for the anomaly detection: originates check, frequency analytic, and time analytic. And both the analytics are new techniques that we developed in our system that haven't been used before. I won't go into the details of each of these techniques, but the key insight behind both the analytics is that attacks are usually infrequent and short-lived compared to benign announcements. We evaluated our system from February to May last year, and we injected 9 simulated attacks into the data, the length of frequency of which are modeled after past real-world attacks. We also performed a real-world attack, like ethically, to evaluate our system. Here are the results. Both the frequency analytic and time analytic have really low false positive rates, and both of them were able to detect the simulated attacks and the real-world attacks that we performed. The results for these analytics highlight an important characteristic about the Tor network, that most Tor prefixes are relatively stable compared to the rest of the internet, that they're announced by a single AS in all their updates. This is the reason why the analytics are able to detect the attacks, whereas at the same time having low false positive rates. Those are the 3 parts of our work. In summary, we performed the first measurement study to understand the vulnerability of the Tor network to active attacks. We found that high Tor bandwidth relays may have low resiliences. We also designed a new guard relay selection algorithm to protect Tor users from being affected by BGP attacks. And we deployed a live BGP monitoring system to increase the routing transparency in the Tor network. We also have our project website there. That's the link on top of the slide. All the information are there. You're welcome to check it out. We've also implemented our Tor release and election algorithm in the Tor client. The code is up on GitHub. That's the link in the middle. And if you're interested, we've been having some ongoing discussion on the Tor dev mailing list about the potential of actually implementing or integrating these defenses into the live real Tor network. If you're interested, again, please join our discussion on the Tor dev mailing list. That's it. I'm ready for questions.
Can you say a word on counter-RAPTOR's effect on passive resilience? Mm-hmm. So the ability to do correlation attacks?
Oh, yeah, sure. So in order to do correlation analysis on Tor, the adversary needs to be on both ends of the communication. So we're pretty much preventing the adversary from getting onto the client and guard end of the communication.
But you're making node selection more predictable, possibly.
Depending on your definition of predictable, we're using a different way to select guards because right now they're purely based on bandwidth, which is predictable in a different way. Now we're kind of shifting the focus a little bit towards, we're going to pick more resilient relays based on the client location so that chances are that they will have lower chances of being affected in case an hijack happens on their guard. Does that answer your question?
Maybe, but
we can catch up offline.
Do you have any other questions? So you mentioned that you did the real-world experiments ethically. Can you say a few words about what you mean by that exactly?
Sure. So we use the peering framework, which is the same framework I think another paper used. That was like Tuesday presentation, the Bitcoin one. Basically that we have a machine set up at Princeton, and we had a VPN tunnel set up with 2 different ASs, let's say. So we make the announcement through one AS, and then after that, we make the same announcement through another AS that we had VPN tunnel with. And the announcements that we're making is a dedicated IP block that was kind of temporarily owned by us for the sake of the experiment. So no one else is using the IP block, so we are only kind of affecting or hijacking our own traffic.
Very nice.
Thank you.
All right, if there are no other questions, let's thank the speaker.